All right, let's start from linear least squares. Linear least square. So in applying the linear least square approach for scalar parameter, we must assume that it is it is a linear function. S is linear with respect to the unknown parameter theta, and this h has to be a known sequence. Then the reader may want to refer back to chapter 6 of BLUE. Okay, but it doesn't matter here. The LS criteria becomes this, and minimization to be is readily shown to produce LSE like this. But notice that H has to be known. H has to be known. It can be complicated, but it has to be known. So theta here will be something like this. Okay, the thing is you just take the differentiation and take the first order differentiation to 0, and then you get theta. Okay, so you get this. And then it's like a formula. Whenever you have a linear version of the least square problem, you put it in, you get the data. And the minimum LS error obtained by putting this into this, you get we do some simplification, and then eventually we get this. Okay, so you get summation of x squared minus theta, and then theta hat, but theta hat is already given here. Okay, the last step follows because the sum s is 0. Alternatively, by using 8.4, we can write j min as like something like this. Okay, but the point is you get an estimator and you get a j min, and j min is like the performance metric here. It's like a performance metric. So the minimum LS error is the original energy of the data less due to the signal fitting. Okay, this is the energy of the data minus less 的意思就是减去的意思这个 less 就是减去的意思 less this energy signal data energy less what less the estimation due to signal fitting. And we have, for example, if theta is equal to a, we have h equal to 1. That is what? That is a DC level problem. Then we have a hat equal to x bar. And we have j min like this. We have j min like this. If the data were noiseless so that x equal to a, if x is equal to a, then what? Then j min is equal to 0. Or we would have a perfect LS fit to the data. And this is reasonable, right? 如果你 DC level 的问题本来就没有 noise，那你取 x bar，你会得到一个完美的 A 值，所以其实它的 J 就会是0，也就是它没有 error。那当然这是一个极端的 case 极端的 case。On the other hand, if x is equal to a plus w, where e is larger than that, then this is larger than that. The minimum error would be something like this because this is small, but it can be approximated by that. So let's take a slight change of the model. If we have a vector version theta, we talk about scalar version of the theta. Now, if we talk about what? We talk about this vector version, then the linearity would be described by this, right? This is a matrix form for linearity. That also comes from linear algebra, where H is a known M by P matrix of four rank P. The matrix H is referred to as the observation matrix. Why? Because if we take a look, you're trying to observe H through H. No, observe theta through H. 如果你要观察 theta，你当然直接观察到 theta 是最好的，所以就是 S 等于 theta。可是常常我们的系统蛮复杂的，不管是讯号处理、通讯控制系统，我们观察到的资料通常不是资料，观察到的这个所谓 theta 通常就是经过一个系统观察的函数可观察到的。这里还算是好的，因为这里是线性的，很多观察的行为其实是非线性的。Okay, so this is of course the linear model. Okay, the linear model without the PDF assumption. So we take the j x minus this. But x minus this, if you take a matrix form, it's going to s is like s is here, right? S is here. So you put s in here, write it in the matrix form, you get this. So your j becomes something like that. So you do matrix format, matrix version, the differentiation, you get that. And then let's make a simplification, and eventually you get estimated like this. That is a vector version. Then how about J-mean? J-mean is a perform， 就像我们其实常常在谈的，我们谈完一个 estimator 之后，我们会想要知道它的 performance。那因为这里它其实是没有，通常对于 noise 的几率是没有假设的。没有假设的话，就是没有办法去算它的 expectation 啊 variance 那些，所以我们只能算它的 J-mean。So we will calculate J-mean, and you get this. But you have theta hat, right? You have theta hat already obtained. So you put it in, you get like this. You get this. But there will be some mathematical simplifications, but it's fine. It doesn't matter. But another version is if you have a S problem that is weighted by W, weighting matches W, so that J theta is like this. And if J W is diagonal with diagonal elements J theta, then it will become this. 这就是有权重的版本了。为什么会有权重呢？在某些问题里面，我们会发现说，我们想要某些值是比较重要的。为什么？譬如说，我们要 estimate 一个值，那它随着时间的流逝，我们当然会觉得时间比较近的是比较关联性比较高的，所以我们给它权重比较重。譬如说，举例来讲，我们要预测明天的气温的话，我们会用今天的气温、昨天的气温、前天的气温一直往前推，但是你会知道越近的关联度越高，所以你会想要让它的时间比较近的权重比较高。OK， 所以这个只是个例子，但是也很多问题有这样的特性就是你想给它权重。Okay, then this weighting, how do we determine the weight? And we have to mention that in many cases, such as this one, we actually do not have a good answer for that. We don't have a good answer for how to choosing the weight. The only thing we can do is by experience, by rule of thumb, by empirical experience. Okay, so this is how we do it. So this is a weighted version. Then, but notice that this is diagonal only. If it's not diagonal, then W is over here. You have to do the whole minimization for the whole thing. It will not be that simple because of diagonal elements. Okay, so But if it's diagonal, then it becomes like this. Then the estimator becomes this, okay? And then we're happy because we have a solution for that. At least we get a solution, okay? Now, this familiar estimator is, of course, the blue things up. Wn is uncorrelated, so that Wc minus 1. The general form of weighted LSE is readily shown to be like this. The general form of the weighted LSE, what? This one. It's readily shown to be like this. And its minimum LS error is like this. Then uh, this geometric interpretation is uh, if we just denote columns, we write down its columns, and S can be written in this form, So its interpretation is we think of this as the signal vectors H. So for example, Fourier analysis, you have this, you want to calculate A and B, but the basis is already known, right? Because they are already defined. So you have S equal to this Fourier basis multiplied by A and B, and then you do this J, okay, this H1, H2, S is like this, and you have J, and you have this, okay? This is what? This is the Euclidean length. But anyway, the J is written in this way. So this is to say that we are using H as the space. H as a space. Uh, in, in other words, H is the basis to form the space. The basis to form the space. And we are trying to find out the theta, the A and B, which is the theta in this case. Okay, so this is the Fourier series expansion. But I think conceptually, understand this is important. You understand this is called signal space. And signal can be orthogonal and non-orthogonal if you put it in a vector space. Okay, I think that's the end of this session, and we'll continue next.